Question number 1. What subshells and orbitals are available in M shell, and which of them are degenerate orbitals for hydrogen atom? So the principal quantum number n is also called shells. N equals 1, K shell, 2, L, 3 is M. So M shell principal quantum number n is 3. And when n equals 3, L can be 0, 1, 2 until n minus 1. So here are 0, 1, 2, which are called S orbital, S subshell, P subshell, D subshell. And in each subshell, you may have many orbitals. When L equals 0, M can only be 0, that's 1 orbital. When L equals 1, M can be 0, positive, negative 1. That's 3 orbitals. Okay, so you can, 2 ways you can write the orbital. 3s or psi 300. 300 means principal quantum number 3, angular momentum quantum number 0, and magnetic quantum number 0. Okay, similarly, for p orbital, you can write psi 310, 311, 31 minus 1. For the 5d orbitals, okay, you can either use this symbol that we usually use, or psi 320, 321, 32 minus 1, 322, 32 minus 2. Okay, so the last one, those are quantum number m. Now, what are degenerate orbitals? Okay, so all these orbitals, they have the same energy because principal quantum number is 3. For hydrogen atom, energy is determined only by principal quantum number. So therefore, the degeneracy here is 9. Question number 2. Write down the expression for radial distribution function of 2s electron. Now this can be easily found from either textbook or my lecture notes. And you look at R20. 2 is the principal quantum number, 0 is L. So when L equals 0, that's s orbital. And the question is locate the radial nodes. So that means this is 0. And constant can't be 0. Exponential function cannot be 0. So the only way to make this 0 is A equals 2A naught. And this is a drawing of this radial wave function. And it changes sign from positive to negative. And here is the distance 2A naught, where the wave function is 0. Next, determine the radius at which electron is most likely to be found. So to find the distance for the most probable wave function, probability, you need to look at the probability distribution function, not the radial wave function itself. So it's the radial wave function squared, radial function squared times r squared. All right, that's this function. Okay, simplify, and you get this function. Okay, and in calculus, to find the most probable distance, you need to derivative this function and let this 0. And so I will skip the steps, but I really strongly suggest you try it. And you should get this function, this equation. And so let this to be 0. Again, constant cannot be 0. Exponential cannot be 0. So this can be 0, and this can be 0. So you have 2 solutions. Okay, 0, 2A naught, that's for this function. And 3 plus minus square root of 5A naught, that's this function. Okay, so you have 4 solutions. Maximum or minimum. Okay, here is a drawing. All right, and in this drawing, you have 2 maximum. You have 0. So here, R is 0, and R is 2A naught. These are the minimum, and the maximum is small maximum 3 minus square root of 5A naught, and this is the solution. The most likely to be found, the distance is 5.24 A naught. Question number 3. The following is a wave function of hydrogen atom. Specify the values of N and L. We look at the symbol psi3pz. 3 means principal quantum number is 3. P means angular momentum quantum number is 1. So N equals 3, L equals 1. Locate the radial and angular nodes. So this is a complete wave function that includes radial wave function, which is a function of distance, and angular wave function, which is a function of angles. Here is only theta. Now to find the radial node, we let this function to be 0. And just like last question, the constant cannot be 0, exponential function cannot be 0. So the only way to make this 0 is the function 6r over a naught minus r squared over a naught squared is 0. And the solution is 6a naught. So the distance at distance 6a naught, wave function becomes 0. Okay, to find the angular node, you let this part to be 0, and cosine to be 0. Cosine to be 0, theta has to be 90 degree. Now remember, theta is the angle between z direction and the line from origin to the point in 3 space, and so this is the angle. For theta to be 90 degree, that means it's an xy plane. Okay, and therefore xy plane is the angular node for 3p orbital. So how does this 3p orbital look like? You have a radial node that distance 6a naught, wave function is 0, and the angular node that is xy plane. Now we know for 2p looks like this. That's the 2p orbital, and 2p orbital has the angular nodes. The plane xy plane wave function is 0, right? The wave function is maximum along z direction, but 0 in this plane. Now similarly, for 3p orbital, you also can see the plane through the origin, xy plane, wave function is 0. But there's also a difference that it changes sign inside this small circle that is blue and then becomes red. And on the bottom, you have a small red and then becomes blue. The change sign. So there is a distance where the wave function is 0, and that is a spheroid. Okay, the distance is 6a naught. That's the distance. The wave function becomes 0. Question number 4. What is the orbital angular momentum of an electron in the orbitals 1s, 2s, or 3s, 3d? Give the numbers of angular and radial nodes in each case. And so the angular momentum magnitude is calculated by equation h bar times L plus 1. So we need to find the quantum number L. Also, to find the number of nodes, for the angular nodes, the number is L, is determined by L. For radial nodes, is n minus L minus 1. Okay, so let's look at the first one. When the orbital is 1s, s means L equals 0. Okay, and therefore, according to this equation, when L equals 0, L magnitude of angular momentum is 0. So how many angular nodes? Well, L equals 0, so there's no angular nodes. How many radial nodes? 1, okay, principal quantum number is 1, minus 0, minus 1 is, again, it's 0. So for 1s orbital, there's no angular nodes, there's no radial nodes. Okay, let's look at 3s orbital. For 3s orbital, the angular momentum quantum number L is still 0 because it's s orbital, and therefore the magnitude of angular momentum is still 0. Now for the angular nodes, L equals 0, so there's no angular nodes. But what about the radial nodes? Radial nodes is, in this case, n equals 3. So 3 minus 0 minus 1 give you 2 radial nodes. Okay, so how does it look like? Here is a diagram shows the 3s orbital. Okay, so you can see again it changes sign. Inside is origin and then blue and origin. So you have two spheres that the wave function is 0 because the wave function is between the two signs, so it's 0. So you have two radial nodes. Next, for 3D, D means L equals 2, and so plug in here. So it's 2 times 2 plus 1, that give you square root of 6 h bar. That's the magnitude of angular momentum. So how many angular nodes? L equals 2, so you have 2 angular nodes, and the radial nodes is 3 minus 2 minus 1 is 0. So for this wave function, there's no radial nodes, but you have 2 angular nodes. So here are 5 3D orbitals. You can see all of them have 2 radial nodes. Angular nodes, 2 planes. For example, this one has 2 cones that make the wave function 0 between the 2 signs. Question 5. The total energy eigenfunction for hydrogen atom have 3 quantum numbers, and only principal quantum number determines the energy using this equation. So the question is, using the nomenclature listed as eigenfunctions or orbitals that have the following total energy eigenvalue. Remember, eigenvalue is the allowed energies. So for example, let's do the first one. The allowed energy is negative E squared divided by 32 pi epsilon 0 A naught. Okay. Now compare with the general equation. All right. This is a special case. This is a general allowed energy. So in order for the energy to be this equation, you can see n squared has to be 4, because 4 times 8 give you 32. So n squared has to be 4. So what is n? N has to be 2. So for the first case, the principal quantum number is 2. So when principal quantum number is 2, how many orbitals? Okay, the angular momentum quantum number can be 0, can be 1. The maximum is n minus 1, so n quantum. And when L equals 0, m can only be 0. When L equals 1, m can be 0, positive, negative 1. And therefore you have 4 wave functions. So you can write 2, 1, 2, 0, 0, that's this one. 2, 1, 0, that's this one. 2, 1, 0, right? So that's this one. And 2, 1, 1, and 2, 1, negative 1. So you have 4 wave functions. This is 2s orbital. This is 2p, 3 2p. Okay, 2p. One of them is 2px, 2py, and then 2pz. And they all have the same energy because the principal quantum number is 2. Right? So they have, so the degeneracy is 4. Let's look at the second one. And in order for the energy to be this equation, n squared, okay, must be 9. 9 times 8 give you 72. So n squared is 9. Therefore, n equals 3. Sorry, n equals 3. So what is L? When n equals 3, L can be 0, 1, 2. So that's 3s orbital, 3p orbital, 3d orbital. Okay, and you know 3p, you have 3 of them. M equals 0, positive, negative 1. All right, d, you have 5 of them. So here are the symbols or nomenclature. So 3, 1, 3, 0, 0, and that's 3s orbital. 3, 1, 0, 3, 1, 1, 3, 1, negative 1, that's p orbital. And then 5 d orbitals. And all of them has the same energy. all of them have n equals 3, and so the energy are the same. So degeneracy is 9.